introduce myself. I'll introduce myself. I'm Sean Maxwell with Ahmad Ghassami. We chair the ARMA Technical Committee on Induced Seismicity, and very pleased to continue the webinar series, something we've been working with Jens Lund-Sneed and Madi Haddad at presenting to the community over the last couple years now. I think we're coming up to our second year anniversary soon. So we've had kind of a very interesting set of webinars over each month, and today, no exception. We're very excited to have Jim Dieterich from University of California, Riverside, talking about some of his work. Jim's a pioneer in rate state friction characteristics, and we'll be talking about a case study of applying it to an induced seismicity fluid injection example from Italy. So good to see a slightly different geomechanical modeling kind of concept, if you like, and also be interesting to virtually at least travel to Italy for this case study. And we thank Jim for agreeing to do the webinar today. So just before we get started with Jim, though, we've got just a few things we want to cover. So we want to talk about upcoming presentations, webinars. So I'll pass it over to Jens to talk about our upcoming schedule.
Thank you, Sean. We have a number of presentations lined up now through July, and I'll just list what a few of them are. They're going to be the first Friday of every month, as is usually the case, at 10 a.m. Central, I think in all cases. Starting with Cody Comiskey of Chevron and the Texoga working group, he'll be talking about the newest report on update on seismicity responses specifically for the Permian Basin. And the following month, in the beginning of March, we will have Tim Kniefsey, who directs the EGS Collab project, and Martin Schoenball, formerly of the EGS Collab project, talking about their efforts to use a natural laboratory to induce small earthquakes. The following month in April, Amanda Grieg, this will be the second week in April, of Ovintiv, we'll be talking about induced seismicity in Western Canada associated with disposal. And then Mark Van Dyke of NIOSH will be talking about mining induced seismicity at the beginning of May. There will not be a webinar in June because that is the month of the ARMA annual meeting. But the beginning of July, Rebecca Harrington of Ruhr Universität Bochum, if I'm saying that anywhere close to being right, we'll be talking about slow induced earthquakes.
Great, thanks, Jens. And just to quick comment on the schedule, as you said, Jens, we'll skip June to avoid conflict with the ARMA annual symposium that'll be in Santa Fe this year. But the committee's looking at a workshop that we'll be putting together in association with that symposium. We're just waiting to get kind of clarity on ARMA's vision for the symposium, and then hopefully next month we'll share some ideas we have for the format for that workshop. I'll pass it over to Madi to talk about the rule.
Sean, this is Peter. May I just have one quick sentence in here?
Yes, please, Peter.
On the symposium, we have reached a decision that the symposium will be live. It'll be person to person. And we are probably going to have pre-recorded presentations from authors whose papers are accepted, but they cannot travel, primarily from China and certain other countries. We don't know what the situation will be in terms of international travel, but you can count on Santa Fe taking place in person unless there's a legal requirement that says we can't do it.
Well, that's excellent news. Thank you, Peter, for the update. If you don't know, that's Peter Smealy, who directs ARMA. And good news, the only way to really visit Santa Fe is in person. A virtual visit to Santa Fe didn't seem too appealing, so I'm glad to hear that it's going to be in person.
Yeah, thank you, Sean. Good morning, everyone. This is Mahdi Haddad from the Bureau of Economic Geology. First of all, I would like to thank all of you to attend this another great webinar of Induced Seismicity Technical Committee webinar series. We have a lot of people subscribed to our email list. We have almost 500 people from the academia, from the industry, and from regulatory agencies. We would like to extend this network by letting you share this webinar invites to the colleagues that are interested in this topic. Please move forward and distribute this invitation to anyone who is interested in your company. For better flow of this webinar, we have everyone muted during the talk. Please save your voice questions for the end of the webinar, but during the webinar, you can post your questions in the chat function of the Zoom meeting. And specifically, this Zoom meeting will be recorded also after authorization by the presenter. And all of the recordings will be uploaded to our YouTube channel. Please subscribe to this channel to receive notifications for the future uploads. Without further delay, let's invite Jim to have the stage and present his talk. Thank you, everyone.
Okay, how do I get to my screen?
So if you go to the bottom, Jim, you should see a square, a rectangle with an arrow that's share screen.
Yeah. Okay, there we are.
Perfect.
Great. Okay, so I'll be discussing a rate model for earthquakes, induced earthquakes in this case. And it's based on rate and state dependent friction. And so I guess before I start, I really want to acknowledge both my colleague Keith Richards-Dinger, who made a couple of contributions to this presentation, and to the this Valdorri team from Italy and the US that looked at the induced seismicity. So there we are. Okay, sorry for the delay there. So the background on this, I'll spend a couple of minutes on rate and state dependent friction, since that is really the basis of for the formulation. I think some of you might be familiar with it, but many may not be. And then I'll go on and show how we turn that into an earthquake rate model. And I'll say a couple of words about the pressure diffusion model that I used for the simulations that I'll be talking about. And then as regards simulations, I'll first talk about just some general characteristics of induced earthquakes by fluid injection as represented by this model. First some simple models and then some slightly more complicated models. And then finally, I'll talk about an application of this model to induced earthquakes at the Valdorri oil field in Italy. So this is the kind of the basic equations for rate and state dependent friction. Shear stress during slip is a typical friction law, coefficient of friction and normal stress. This is the formulation for rate and state dependent friction. There's a mu sub 0 is kind of a reference coefficient of friction. And then these are perturbing, they have small values, but they're perturbing coefficients, both for direct sliding rate effects. So del dot is slip rate. There's a direct sliding rate effect. And then there's the state effect that's represented by the state variable theta. And from experiments, we derive an evolution law for theta, which depends upon time, slip, and changes in normal stress with these various coefficients. P sub c is an important one, and I'll point that out in a moment. So here's some very old work back to 1994 I did with my colleague Brian Kilgore. And these state effects are visible, become evident in two types of experiments. The primary experiment is stepping from one slip speed very quickly to a different slip speed. And this is the ideal representation as given by these equations. And what you see is if you suddenly slow down, the stress drops, but then it rises again to a new level, steady state level. And then if you speed up again, you see the opposite jump and the decay. These jumps in strength are due to this term here, this direct sliding rate dependence. And then this evolution of friction with time is given by this evolution law here. And as you see, these rate and state effects are really characteristic of a very wide range of materials, a surprisingly wide range of material, not just rocks, but glass, plastic, this is Teflon and steel, even blocks of plywood sliding against each other. It seems that most materials that have non-polished surfaces, kind of rough surfaces, or gouge, here's granite with gouge, have these rate and state effects. Another manifestation of this is the slide, hold, slide experience, where we slide for some distance, stop the sliding, and you see a relaxation. And then, but when we reload, start sliding again, we see this peak stress. And the peak stress is proportional to log time, which is given by this term. So this is kind of old work. But what we've done is we can scale this up, and there's an interesting, some interesting properties associated with rate and state friction. One is that when we use those equations with models for the onset of unstable slip, in this case, earthquakes, we find that there's a period of accelerating creep prior to instability, always, and that instead of a single threshold stress for the onset of unstable slip, that there's a wide range of stresses. So there's no longer a single failure stress, there's a range of stresses, and the time to instability is highly time dependent. So we can use the rate state properties with a simple spring and slider and come up with another formulation for another evolution law. And this is for the evolution of slip speed prior to unstable slip. And I won't go through the details, but you'll see it has the same form as a state variable form for friction. And we can get solutions then for how slip speed, and time to instability from some initial conditions. These relations were verified with this apparatus that we put together at the USGS many years ago. It's a very large scale biaxial apparatus. The sample size is about 1.5 meters square and close to 0.5 meter thick, with a synthetic fault down the middle, and it's with instrumentation, strain gauges, and displacement transducers. And this is the kind of record that we see before every unstable slip event. So these curves here represent different locations on the fault. The green curve is slip here at the center. And what we see is accelerating slip prior to instability, and it occurs over some finite zone. And that accelerating slip is very well with those solutions for nucleation of slip that I showed previously. The data points are from experiments, and the curves are predicted by those equations that I showed a couple slides back. And the different experiments here, I think the most interesting one perhaps is shown by the red dots. This nucleation, once it starts, is self-driven. And so in this case, once we started to see the beginnings, very beginnings of unstable slip, of accelerating slip, the loading was turned off, but the stresses held, external stresses held constant. And the slip continued. It was self-driven to instability. And I guess I should explain the axes here. Sorry about that. This is kind of read backwards. This is time remaining to instability. So instability occurs at 0, and it's in a log scale. Oops. And so you see pretty good agreement here with the experiment and theory. So I have quite a bit of confidence that we've captured the basics of the process. Now, kind of scaling up further, we can go from those nucleation solutions to an earthquake rate formulation. This was first published in 1994, so it's pretty old work now. And this formulation is based on the idea that earthquake nucleation controls the time and place of initiation of earthquakes, but it doesn't control the rupture process. So these are nucleation. And so any process that alters the nucleation times controls changes in seismic rates. And for induced earthquake simulations, we've implemented fault models, and I'll show you some with more than 1,000 elements on the fault. So we can see how earthquake rates vary along a fault based on how stresses vary on the fault. And a limitation of this model is that there's no interaction among fault elements. So it's only the external forcing that drives the earthquake rates. And this is what the rate formulation looks like. Again, it has a state variable, in this case, gamma. And you kind of recognize the form of this equation. So this is kind of a rescaling from kind of the micro scale up to the macro scale. And induced earthquakes are, by fluid injection, enter through this effective normal stress term here and here, where the effective normal stress is the normal stress minus the fluid pressure. And a characteristic of this formulation is that steady state, the rate is proportional. The earthquake rate at steady state is proportional to the stressing rate. This rate factor F, Keith Richard Zinger has come up with a evaluation of that based kind of on first principles. So, and it's basically it's a reference rate R divided by a reference stressing rate. So it's just, I think, fairly straightforward. So this is an ancient slide from 1994, and it shows the plot here of earthquake rate versus time following a stress perturbation, a step in stress. And what we see is that there's a jump in earthquake rate. It can be quite extreme for relatively modest changes in shear stress. That's this delta S over A sigma. And then we get a 1/T decay. And if the sample is continuing to be loaded at some rate, then the background earthquake rate goes to the steady state rate as shown before. And but if there's no stressing, then the earthquake rate just continues to fall. This has been adopted as a pretty general model for aftershocks. The idea here is that when an earthquake occurs at some location, it transfers stresses to other locations, and that sudden change, that second stress, then generates those local aftershocks. And you're probably familiar with the Omori's aftershock law. So this is Omori's aftershock law. It's empirical law. It seems to hold up. It's extremely robust. It holds up for earthquakes all over the world under a variety of conditions. And it's an empirical law, just observations. But with the rate state formulation, we can now attach interpretations in terms of mechanical parameters and to the different constants in Omori's law. And it's been pretty widely adopted, this formulation, as a way to model aftershocks. And it's been quite effective, I think it's fair to say. Now, in the simulations I'm going to show in a moment, we use just a very simple pressure diffusion model. And it's based on Wang 2000. And we use it as a Green's function to find the pressure at various distances from an injection point as a function of time. And this, again, this is a solution to Wang's basic solution for Green's functions for pressure, for changes in injection rate. So delta V here is a change in fluid injection rate, the volume, and it's implemented then as a series of, or rather complex injection histories can be represented as a series of changes of injection rates. The other terms here in the equation are D is the pressure diffusivity, X is distance from the injection point to the observation point, and psi is the product of the porosity and compressibility of the media. This assumes homogeneous, it's a homogeneous media, infinite in extent. Okay, so here I show just the characteristics of a uniform constant rate injection as a function of pressure and time at different distances. So a characteristic of the infinite media is that when you inject at a constant rate, the pressures will rise and then go asymptotically to some constant value. And the red dots here are the point of maximum pressurization rate, again, as a function of distance. So pressurization rate is of interest here because the pressurization rate is a primary controller of rates of induced seismicity. So here we have, I'll first discuss just a very simple model, which we ignore any kind of background or tectonic stressing that might be driving earthquake rates. And under those conditions, with no tectonic stressing, we have, there's a maximum and minimum fluid pressure. There's a range of fluid pressures or initial shear stresses under which induced earthquakes can occur. So Tmax, this is simply the steady state sliding friction. The stresses are above Tmax, then you don't, earthquakes will nucleate spontaneously. You get this acceleration of slip with time that culminates in an unstable sliding situation. So this is just a steady state sliding friction. Tmin is the initial shear stress on a fault surface. And that's the minimum initial stress at which some pressure P max can induce earthquakes. And if this initial stresses are below Tmin, then injection of fluids will not result in earthquake nucleation. The key point here is that there's a range of initial stresses under these circumstances over which induced earthquakes can occur by this model. There's not a single threshold. There's not a single threshold stress as you would get, say, from a simple Coulomb failure model. There's a range of stresses under which this can occur. So here's a very simple model. It's got 16 of a fault. So this is a fault surface here. We assume the injection is at some point, in this case, a half a kilometer from the fault surface. And it is inducing fluid pressure changes on this fault surface, which are just represented schematically here. This is a result of a simulation over 10 years using that rate formulation of the number of earthquakes induced as a the rate of earthquakes as a function of time. And this is the red are contours of the pressure change along any profile. Since this is a radially symmetric problem, this profile can be in any direction. But this is, the red are profiles of fluid pressure change, and the blacks are profiles over a wide range of earthquake rates. So it shows that. So it's a fairly simple result. You can see that the pressure rates initially follow the, the earthquake rates initially follow the pressure contours and go from there. Here's a somewhat more complicated model just to kind of illustrate what things look like in the model. Here we have the same injection rate, but with short pulses where the ejection rate is doubled. So we have kind of this pulsed injection superimposed on a uniform injection rate. So we get a jump at the time of a pulse, we get a jump in rates, and then it decays back kind of to this more long-term level. So we get these pulses, results in very complex space-time patterns of earthquake rates, as you can see. So even with a simple model, you can get very complex behavior. Going back now to that range of initial stresses where you can get induced seismicity, this kind of shows that effect here. So this is across the top here, you see these are the initial stresses. They all fall within that range of potentially or potentially inducing earthquakes. This is 1 MPa below the maximum value for the initial stress. And then this is very close to that threshold stress for spontaneous nucleation without any fluid pressure changes. And you'll notice that at lower initial stresses, the expansion of the induced earthquake zone is slower than it is for higher stresses. Also, the onset of seismicity, that's this delay, becomes shorter as you increase the initial stresses. And this shows the number of earthquakes versus time. This is the time of shut-in here. So this is injection for 5 years, and then shows what happens for 5 years after shut-in. And so and as you see, with higher stresses, you get more seismicity following shut-in. That's evident in this case here. So at the time of shut-in, the earthquakes don't stop immediately. They continue for some time. Now, in this model, continuing seismicity following shut-in can arise for 2 reasons. First, because of the delay in the pressure diffusion signal, the shut-in signal. But the second one is because of the time-dependent nucleation. Some of these earthquakes may be essentially like aftershocks to the pressure perturbation instead of aftershocks to the stress perturbation in a normal main shock aftershock sequence. We'll take a look at that a little bit more closely in a few minutes. And then so here is again looking at the duration of seismicity following shut-in. The longer you inject, the longer the post shut-in seismicity. So these red dots are the time for seismicity rate to drop by 50% following shut-in. So this is a fairly simple model, but it kind of gives some interesting looking results that may kind of illuminate some features of induced seismicity. Now, it becomes a bit more complicated when there's background stressing, say tectonic stressing. And so I'd like to talk about that for a minute or two. This is just to refresh your memory on what the rate equations look like for earthquake rates. So again, earthquake rates. This term here is this F term. It's just a scaling term, and gamma is this state variable that evolves with time. Now, a characteristic of the evolution equation is that the earthquake rate will evolve with time to a steady state rate. So this steady state earthquake rate now is proportional to the tectonic stressing rate. And again, we can solve for F as a kind of based on first principles, which is a scaling term for what the earthquake rate is, given some B value and some minimum observed magnitude, kind of what the expected earthquake rate is as a function of stressing rate. And this is a plot of the steady state rate. So this is log stress rate in megapascals per year against log of the earthquake rate for different magnitude thresholds, assuming a B value of 1. This is a Gutenberg-Richter B value, and an earthquake stress drop of 4 megapascals. These curves move up and down as these parameters change. Now, to give you an idea, kind of turn this into reality a little bit. What I plotted here is the some different areas. So this is not a data point. So SA, that's roughly the stressing rate that we have along the San Andreas fault system. And then this is the log earthquake rate per square kilometers of fault per year. So kind of San Andreas, these are kind of, so that's fast tectonic, what I term fast tectonic. In this area, for example, Italy, and I'll be talking about that in a few minutes, it has stressing rates that fall in this range. And so you can get an idea of what the seismicity rates on faults are from that. And again, down here are kind of more stable areas. I put stable in quotes because I'm skeptical that any area is truly stable. For Australia, Scandinavia, and parts of the US kind of fall in this range. Now, once you get down to these really slow rates, they're very hard to measure, or if impossible, with current technology, geodetically. And the seismicity rates become very low. And just for example, this point right here for earthquake's magnitude 1.5 and larger, you only get 1 earthquake per square kilometer of fault in 25,000 years. So to me, what this says is that the fact that an earthquake has not been observed in some area does not necessarily mean, in historical times or instrumental observation times, does not necessarily mean that that it's not being stressed and it's totally aseismic. We just haven't been able to watch it long enough to see if there are earthquakes there. So with that as a basis, we can talk a little bit about detectability of earthquake rates and kind of also explore a way to regularize the model computations, particularly in areas where we don't have data that where earthquake rates are very low. So I'd like to introduce the concept of detectability of induced seismicity. And for the purposes of just kind of illustrating kind of this idea, I would argue that since the background rates, they certainly fluctuate with time, even and that's evident in highly tectonic areas, that to detect induced seismicity, it probably has to be at least 10 times the background rate, perhaps more. And in addition, that level of seismicity has to be greater than some level, some base level here. which is this. And again, for the purposes of illustration, given that induced seismicity typically occurs over small areas and involves short periods of time, geologically speaking, I've just I argue here that the earthquake rate has to be at least one earthquake in 10 years per kilometer of square kilometer of fault. Now, with that background, then we can determine from the rate equation what change in pressure is necessary to have detectable induced earthquakes. My argument is that any change in fluid pressure will change earthquake rates. But the point is, at what point does that become detectable? And we can solve for that. And immediately from this equation, we get this general, since sigma 0 here is the effective normal stress on a fault, that the threshold for the pressure threshold for having detectable seismicity, that increases with the effective normal stress. So shallow earthquakes are much easier to or trigger more earthquakes for a given pressure change than deeper faults. Probably fairly obvious. Okay, so in the literature, we often, for induced seismicity, we often see plots that look like this, where the horizontal axis is time. In this case, this is 10 years. This is time in seconds. 10 years. Earthquake events then as a function of distance from the injection point. This, in fact, is a model result. This dotted curve is the arrival of the pressure front from a point source of injection. And in this case, the fault is half a kilometer from the injection point. And the heavy dashed line is this delta P to reach detectable seismicity. It's this delta P here. And again, in the literature, there have been attempts made to use kind of an envelope containing the observed seismicity to estimate the pressure diffusivity. And I'm going to argue that that's probably not going to work, because this pressure front, it does depend on the pressure. So this curve, the arrival of the pressure front, that is solely a function of the pressure diffusivity term D, but it's quite different from the front, the earthquake front, where you can observe seismicity. Now, I'll say that this is a model result, and it's based on this, which is shows contours of pressure change in blue and seismicity rate in red. What I've done to generate this synthetic catalog is randomly draw events at different locations on the fault at their underlying rate. So we can generate a synthetic catalog in that way. Now, I'll show a series of 3 figures here, and to show the effect of the kinds of effects we might see in different areas, ones with nominally stable areas with very few background earthquakes, moderately active tectonic regions, and then very active tectonic regions. So I'll kind of show how the seismicity, induced seismicity, would change for a point injection some distance from a fault. And in this case, it's a 10. This is that space-time plot of seismicity, where this distance is the distance from injection to a point on the fault. And this is a map of the fault, with the red dots showing these randomly drawn earthquakes at the underlying rates. So this is the pressure change needed in a stable area, and this is what the seismicity looks like. The expected number of tectonic earthquakes in this 10-year period is less than 1, so it's negligible. And we see that the seismicity is very tightly contained in this simulation. So here's moving up to kind of what I call slow tectonic area. Here, the background seismicity on this 10 by 10 kilometer fault is about 1 earthquake per year, a total of 10 earthquakes in this simulation. And again, this is the pressure needed to reach the detectable seismicity, just based on that kind of arbitrary decision I made earlier on. I'll just go back to it real quickly here, based on these criteria. And then finally, for a highly active tectonic area, we see very high level of background seismicity, about roughly 100 events per year, 10 by 10 kilometer fault. And again, here, this is the threshold for detectable induced seismicity. It kind of gets lost out in here. But I think if you look at this figure, the map of the fault and where earthquakes would nucleate, you can see that there is this circle here represents this detectable pressure change at the end of the simulation. But pretty hard to particularly late in the injection to see what's going on. Okay, so now looking at what happens with shut-in of injection, it gets a little more complicated. Again, we have the arrival of the pressure front that's shown here in this dashed line. Blue is the curve for change in pressure for detectable induced seismicity. And then this curve here is the peak pressure. So after shut-in, with increasing distance, the pressure starts to fall. And the interesting thing here, I really want two things I'd like to point out here. First, notice that there's a gap in this area with no earthquakes following shut-in, but there are these earthquakes that occur as the fluid pressure is falling. In fact, the fluid pressure is falling faster than the tectonic loading in this case. So in all cases, these are, except for these 2 events right here, these earthquakes are occurring as the stress is dropping. And that's purely a rate state effect. So these are essentially aftershocks to this peak pressure perturbation. And I didn't run this simulation long enough to see how long these go on, but just for computational reasons, we can do a similar simulation, but in this case, we increase the diffusivity, so the pressures change faster, and increase the tectonic stressing rate compared to this other simulation. So in this, so the pressure front, and these have much steeper curves, but here you see that the red events that occur as the total stress is falling, go on for a finite time. And so these events out in this area at these times, this is the tectonic stressing taking over again compared to the fluid pressure perturbation. The gap in events here close in, which is smaller in this area, it's kind of confined to this area. This arises because the pressure is falling so fast that it actually quenches the nucleation process. Earthquakes are starting to nucleate, but then they're turned off because the pressure falls fast enough to actually quench that self-driven nucleation. And this was just kind of an exploratory model comparing 2 situations where we have the same volume of fluid injection over 5 years, but in one case it's pulsed it's in 5 different pulses of fluid injection. In this case, it's steady fluid injection. And in the pulsed injection case, we get more earthquakes. These are the synthetic earthquakes again, of course, over 1,200 versus about 900 events. So about 300 different, about 300 extra events for pulse injection. And it seems to be in this model, at least, it seems to be due to an increase in these number of post-peak earthquakes that occur as the stresses are falling. And this is a relatively modest pulsing. Typically in the injection operation that I'll show you in a few moments, the rates of injection are very over a very wide range. And so a general lesson here, I guess, is that if you believe this model, is that it's better to inject at a constant rate than to pulse it. You can get many more earthquakes, particularly with sharp pulses. Okay, get a drink here. I'd like to talk about kind of a study that I was involved in, which is induced seismicity at the Valdorri oil field in Italy. And quite a few people are involved in this. The oil field operators, ENI, they brought in an outside team to look at, this is alphabetical order. They brought in this outside team to look at induced earthquakes that are occurring in their Valdorri oil field. And we had a publication describing this overall study that came out in Nature. This is the reference to it just this past summer. And so I invite you to take a look at that for more details. This is a very wide-ranging study over a lot of different topics. I will talk only about the application of that rate model to the induced earthquakes at the oil field. So I'll not give you a comprehensive overview of that study. So this is an earlier study that it was recognized for some time that there were induced earthquakes occurring at the Valdorri oil field. The oil field is in this area. This is an earlier publication from Butinelli and others. And so there's this cluster of earthquakes here around an injection well. And I have a little better figure of that. All right. So this is the setting. The oil field is down here in boot of Italy. And these are maps of the strain rates, current strain rates as measured in Italy, and the extensional strain trajectories, which I convert to stresses here, and the oil field is right here. So you see it's being extended in a northeast southwest direction. And it's at a fairly moderate rate. So this is a figure from the Nature paper of the oil field. These lines here are the S3, the extensional stress direction based on borehole breakouts across the oil field. This is the oil field here. Here, and this is this little area around Valdorri with the cluster of earthquakes that are occurring in that area. At Valdorri, a non-productive oil well was being used to inject wastewater that was co-produced from the producing oil field. For those of you that aren't familiar with the Valdorri oil field, I believe this is the largest on-land oil field in Western Europe. Of course, the North Sea fields are bigger, but it's a very important oil field for Italy. This is cross section across this through here, which goes through the area of induced earthquakes, and this is the injector well is Cosmolina 2, and it's ejecting into these Apulian carbonates, which are the producing horizon in the field, and some of the earthquakes are plotted here. This is a map of that same area with the earthquakes, and you can't quite make it out, but this brown area is a fault. This fault here, outline of that fault. Okay, a little simpler diagram of the cross section through that area with the injector well here and the seismicity, and this is the Cosmolina fault here. It abuts against this much larger fault here and some smaller secondary faults. The Apulian is the producing formation here, and above that is the Irpina formation, which forms the cap rock, and that's the top of the Irpina there. And this is a cumulative seismicity versus time for magnitude 1.4 and larger earthquakes. An interesting thing is, even though it's roughly a kilometer from the injection site, earthquakes were detected in about 1 day from the start of fluid injection. So it's thought that there was it's a carbonate sequence. So it's thought that there were some very cavernous structures that conducted the fault fluids to the fault quite quickly. Yeah, this is from the Nature paper, a little more colorful diagram. This is the Cosmolina fault here, and the various producing wells and the earthquakes. This the Magorno, I have to get this right, Magorno-Mandrano fault is this one in gray, and it's thought to be the source of the 1857 Basilicata earthquake that killed roughly 10,000 people. So I think that nearness to this very destructive fault, the nearness of this induced earthquakes to that fault I got a lot of people's attention, and there's one reason why this working group was formed to look at the induced earthquakes. For me, this is a little bit easier. So this is a perspective view of the faults in the system. The oil field is roughly in this area here, and then a digital version of the Cosmolina fault, which appears to be the fault on which the induced earthquakes are occurring, and then that I use to simulate the earthquake activity. So the simulations that I'll show are based on the oil company detailed pressure diffusion model of the Cosmolina faults. So I did not do any of the fluid pressure calculations, and this is the pressure change projected onto the fault from 2006, the start of injection, through 2017. And the injector well is located here. And it's thought there's a fault has been detected, this F10, and it's the injection is virtually on that fault. It's thought that that fault conducted the fluid very rapidly. In this case, or conducted the fluid pressure. In this case, in less than a day, it was sufficient to actually start producing earthquakes on the fault. And
Sorry, Jim, just quickly interrupt, just
Sure.
have a time check. So
I'm
you're
just
5
about,
minutes before the hour.
I'm
and-
just about done.
Okay, great. Thanks.
So here it is. Here's the bottom line. Here's the black. I'm sorry. The red is the observed seismicity near at Cosmolina, and the black is our model fit to that seismicity. It's not a unique fit. Mu is a coefficient of friction. A is the rate state parameter A, and with different combinations of coefficient of friction and A, we get essentially identical fits. And then we also so this is an extrapolation at 2,000 cubic meters a day, which is kind of what they're holding to now, and what would be expected to happen for higher injection rates. And I'll just finish up here with this. This is the computed earthquake density from the model for the period 2006 to 2010, with the observed earthquakes overlain, and the computed earthquake rate 2010 to 2017, with the earthquakes in that period printed on that. You see some expansion. There's some uncertainty in earthquake locations. Also note that the earthquake density is much lower for this later period than it is for the earlier one. These are just details, and so I'll just summarize with this. For the Cosmolina earthquakes, the simulations are in pretty good agreement with the seismicity. The free parameters that went into those simulations are reasonable. They're certainly not crazy, and the fluctuating injection rates at Cosmolina led to very complex patterns of pressures and seismicity. And we do see at Cosmolina that during intervals when the fluid pressures are dropping, the earthquakes are continuing, and this can be attributed then to this rate state continuing earthquake nucleation. So I'll stop there. Thank you very much.
Great. Thanks, Jim. Really great presentation. Interesting overview, a lot of really interesting comments, and the case study is quite interesting as well. Just looking at the time, it's the formal hour is almost up here. There's some questions on chat we can go through here in a minute, but just in case people have to drop off, I'll just maybe kind of wrap up the formal part, and then we'll continue on with the Q&A here for a few minutes. But first of all, thanks, Jim, for taking the time for the excellent presentation. And a reminder to everyone, next presentation is, I believe it's February 4th. Perhaps Jens or Madi could correct me if I had that date wrong, but Cody Kaminsky will be talking for the Texoga Induced Seismicity Working Group to give an update on seismicity in the Permian Basin and some of the latest regulatory actions that been playing out there. So again, thanks everyone for their dialing in and listening to the Jim's webinar here. All right, Jim, so if you don't mind, I can read off a couple questions from the chat window, and then
Sure.
Once we go through that, maybe open it up if anyone wants to jump in and continue the Q&A. So Ryan Schultz has the first question, which is thinking about earthquake to earthquake interactions and wondering about stress transfer along the fault. And he's wondering how those sorts of interactions and factors might impact the modeled spatial temporal activity rates.
Yes, so that's a really important point. We have another simulator, which is much more computationally intensive, called RSQ Sim, which actually includes, it simulates specific events and includes interactions. And the earthquake interactions and stress transfer due to those interactions, of course, is important. Generally, what we see is that the interactions increase the overall seismicity rates, but don't really change the patterns. But that's a topic of ongoing study, concern, and interest for us.
Excellent. And that's a good transition to the next talk that's asking about our RSQ sim, actually. So Zijin's wondering a little bit more about the fault model and how the event locations are determined, and whether or not RSQ sim was used for some of those examples you were describing.
So, so RSQ sim is a simulator we developed. It's a rapid simulator that actually simulates rupture propagation, but it's fast. It can do 100,000 events, but it's a supercomputer type simulation. The results I showed here just took the earthquake rates and then drew events at random to build a catalog. And so the catalog has no magnitudes in it. It's just the event locations and time. If I go back to this is our RSQ sim model of the entire oil field. It's not been used to study as of yet, the injection-induced earthquakes. While I'm here, I forgot to acknowledge E&I, the oil company that's been sponsoring this work. They've been marvelous and very open, as evidenced by the publication that came out this summer with what's been going on here. But I'm a little bit reluctant to say anything about what we've done with RSQ Sim since it's not been published. And I need to respect confidentiality agreements.
Understand, yeah. And then I guess Andy Barber, moving on, Andy Barber's got a question here. He first comments that it's a great talk and thanks you. And then I guess the question is the A parameter for the model for the study region, how it was selected, and if there is any borehole sample testing to try to validate it.
Yes. So the A parameter, typically in experiments over a variety of rock types, it's varied. It varies from 0.005 to 0.015. So it varies over, it's a very small number. So it's just a perturbation on the friction, but it varies over at least a factor of 2. The numbers that I use all fall within kind of that range of values. And there are studies going on. I don't know if they're in the public domain yet of the appropriate values for the oil field.
Excellent.
Sorry, I'm sorry, I can't be more specific.
Understand. So I guess I'll ask a question myself, and then we can maybe open it up if anybody wants to kind of continue the dialogue. So I was intrigued with your concept of post-pressure as the pressure was coming down. I don't know if this is the right term, but a post-pressure kind of aftershock sequence that you were describing. And I was wondering if you, just thinking about a fault system, we've seen in a number of places where both SWDs and hydraulic fractures are inducing events, sometimes along similar structures, and obviously with a different, maybe not stressing rate, but pressuring rate between the two, with hydraulic fracturing obviously being a higher pressure perturbation. And I was wondering if for the same fault conditions with that, if you had a higher pressure perturbation and then falling, if you might expect a difference in that post-peak pressure decay rate.
Yeah. So I'm pretty well convinced that this delayed nucleation process exists and will get it and is different from the continuation of seismicity due to delays with pressure diffusion. I think that the key point is this area here where the pressures fall so rapidly that you get a quenching of this earthquake nucleation, this kind of self-driven nucleation process here. And it's just a much smaller region in this area here. So I can only speculate that in areas where the pressures are very high, injection pressures are very high and then shut in, that you may get much faster pressure decay rates. And so that may increase this amount of quenching that happens for this time-dependent nucleation. We've not looked at that at all, but frankly.
Okay, thanks for that. And I guess another question's on the chat. Luigi and Prana has asked a question. Luigi, do you want to just unmute and ask it yourself?
Hello, everybody. I would like to know, due to the fact that the monitoring system changed in time close to Cosmolina well, and we observed significant changes in the magnitude completeness of the catalogs that we published. So, and that you used. I wonder how do you manage this problem? The fact that the earthquake catalog is characterized by strong change in times of completeness.
Yes. So here I relied on the seismologists that are part of the team. And so this fit is based on the ENI catalog that's been vetted. So it's not essential that the catalog be complete, but changes in completeness are important. And this uses the ENI catalog that was, as I understand it, that network didn't change much with time. And so the expectation is that the level of reporting with time is consistent. But you do see that early on, I'm personally a little bit skeptical of the catalog early on. And you see we have some kind of funny behaviors here, very, very rapid increase in seismicity and then slowing while the model predicts a less rapid early on and then faster later on. So I'm a little skeptical of the catalog early on in this series. And for that reason, I did not use a formal fitting procedure because I felt that we were most interested in the we were most interested in the extrapolation there it is, later on where the network was more stable. And I didn't want these early misfits, the model to work on these early misfits where the catalog might be a little questionable and distort what's happening later on, which is of most interest, but what's going to happen in the future here. So that's perhaps not a very satisfactory answer, but it's the best I can do. I took the catalog as given to me with the assurances that that's the best that they could do with it. So.
Perhaps the cause of the strange rate at the beginning could be the very low injectivity of the well at the beginning of the injection test. Perhaps.
Yes.
Okay.
I believe there's some evidence that the diffusivity changed somewhat with time as injection proceeded with the well. And also during this period, there were different kind of well treatments that went on.
Okay, thank you very much.
See, Ryan Schultz has turned his camera on, so he's either showing off his goatee or maybe has a question. All right.
Maybe both. I definitely have a question though. So the first one is just a simple one, Jim. Well, first of all, actually a very, very nice talk, Jim. I very much enjoyed this. If you go back to the slide you were at before where you had the Shutin earthquakes, I noticed, maybe I missed this, but you had labeled a bunch of them red, which were being these kind of aftershock likes. Keep going back, I think it's still further. This one here. And the right panel at the top right, a bunch of those are gray. Are those actually like still stress increasing earthquakes later time after, or okay? So I must have missed
exactly.
This.
Yeah. So there's a background stressing tectonic stressing rate, and countering that, is the pressure drop, and so yes, so all of the black dots in these plots occur as the total Coulomb stress is increasing, and the red dots are when the stress is falling. So it's the combined effect of pressure change and background stressing rate.
So those black dots at the far right on the right panel after the peak P, are those then because the background rate is coming back into play? Okay.
Yes, yeah. So that's the tectonic stressing rate. Now, presumably here where we had a lower tectonic stressing rate, eventually these red dots would convert to black dots because the pressure drop, the pressures would be, the overpressures, or I'm sorry, not overpressures, but the excess pressures due to injection have diffused away. But I didn't run the simulation long enough to find it. That's why I sped up the stressing rate and the diffusion rate, fluid diffusion rate, so you can see the end of that effect here.
Okay, so Jim, just to double confirm how I understand your point here. So those red dots, actually they have Coulomb stress decreasing, but they still happening just because they were on the way.
That's correct.
Okay.
Yes.
Great. Does anybody else have any of the other questions they'd like to ask? Again, feel free to unmute yourself. And
I am also curious about, so I like this model because of the rate and state has that nice link to the decay parameters that you get out of this. I'm curious if you can comment a little bit more about what sort of factors in terms of induced seismicity are going to change those. You did on one of the slides kind of present that the longer that you're going to be injecting, the longer it's going to take for the decay to occur. But I'm curious if there's any other factors that are important that you've seen for your modeling for how that decay occurs or how it changes.
Yes. So the effective, the kind of the background effective normal stress will certainly affect those results. And what else? I think virtually all of the input parameters will perturb these results. But what I presented really is a study in progress. And so there's a lot of things that we haven't explored. Like I want to go back to, I'll go quickly, I think you were referring to this. I want to go back to this case now where there was no background stressing rate. I'd like to re-examine this case now with background stressing, kind of in that, I think, a little more complete analysis of what's going on. Haven't gotten to it yet, so.
Okay, sorry, not trying to grill you. This is just very interesting to me and what I'm interested in too. So
no, I appreciate the question.
Yeah,
thank you.
great. Anybody else like to ask a question?
Yeah, I have a quick question. This is Zohair from Ayash. So this is actually basic. So how do you calibrate DC or characteristic distance for the model?
The interesting thing is that when we upscale the model to larger dimensions, this characteristic sliding distance, d sub c, drops out of the equations. So it does not enter. It's a bit complicated, and frankly, I don't recall the details well enough to attempt to explain where, at what point in the working through these equations, that characteristic sliding distance, which I think you're referring to, drops out. But it does not enter into the rate equations.
I understand. So following with that, another quick one. So you're using a slip rate model, and as you're saying, by scaling up the model, characteristic distance disappears. So how do we know that if a slip is stable or unstable? I mean, the stability of a slip depends on the characteristic distance and also the post-peak slope of stress slip curve.
Yes. Okay. Where the so this goes back to the friction equations, and here's this characteristic slip distance, and it's evident here in this decay distance here, and it varies quite a bit from say with plane surfaces or surface with gouge and so on. So this is what we're talking about. And when we go to nucleation, let's see if we can reproduce this. Here you see, and I'll point out that you get instability. Instability is possible as long as the parameter B is larger than A. That means that the steady state friction decreases with increasing slip speed. So the fault gets weaker the faster it slides over the long term. And when we upscale to nucleation, you don't see d sub c in these equations, and that assumes, and that is because the nucleation is actually self-contained. It does not occur over the entire fault. It's a localized process, and the area over which it's localized scales with d sub c. So in the laboratory, the stiffness of the loading machine is very important as to whether or not you get stable sliding or stick slip when parameter B is greater than A. But in nature, you have these extended faults. And so for small values of d sub c, which are typically measured in, say, less than 10 microns, the nucleation zone is about a meter. If we scale it up for thicker gouge zones in that, perhaps the nucleation zone will scale up to 10 or even 100 meters, but that's still small with respect to the overall size of the fault, say. And so you can always, my argument is that given an extended fault, as long as B is greater than A, you will get unstable slip, but the nucleation zone becomes large. The zone over which that unstable slip nucleates becomes larger, and it is proportional to d sub c. I hope that answers your question.
Yes, okay, thank you.
Great. Well, maybe we'll take the opportunity to just thank you again, Jim, for the excellent presentation. There's a number of thank yous on the chat window. Andy Barber, Chingu, Lee, and Raul. Each thank you. And as I'm sure, I think we've lost a few participants in the last few minutes, but I'm sure I can speak on terms of everyone that was listening to thank you for the material and taking the time to present today.
Well, thank you for inviting me. It was my pleasure. Thank you very much.
All right,
Thank
everyone.
you so much. Thank you for presenting. It was very interesting talk. Thank you.
Okay, so
And thanks, Jens and Madi, as always, for your efforts coordinating this. Appreciate it.
Thanks.
Have a good day, everyone.
okay, I'll
Thank
sign
you.
off.
Have a good weekend, guys.
Yeah, stay safe, stay healthy.
You too.